Alright, in this video we're going to have a look at the problem where we're trying to prove via mathematical induction that the sum of this product of I and I minus 1 is going to be equal to the product of 1/3 n and n squared minus 1 for all positive integers of n. Now, the first step of mathematical induction is to test our first case scenario. In this case, it's going to be positive 1. So if n is equal to 1, we need to test to see whether this is going to be true. So for our first one, this will be 1 minus 1, and that will be equal to 0 when we multiply that out together. And the second case scenario is going to be 1/3 multiplied by 1, and then that's all multiplied by 1 squared minus 1. Now 1 squared minus 1 is 0, and it's the product of anything multiplied by 0, so that's also going to be 0. And because they both equal 0, we can therefore say our first case scenario here is true. So the P of 1 is true. So now we've proven that the first case scenario is true, we now need to assume that the P of k is true. So essentially when we assume that P of k is true, we're looking at the sum of k with I equal to 1 of I minus 1 is going to be equal to 1/3 k of k squared minus 1. Now, the next step on this is to see whether P of k plus 1 is true, which is the next scenario after P of k. But what I like to do before I start looking at that, and I generally do this on a scrap piece of paper, and I find that really, really useful to do it, is to look at what are we actually trying to find when we're doing the P of k plus 1. So essentially, I just like to substitute k plus 1 into the P of k that I've got here. So in this case, I'll just sort of like do it in this area down here. We've got P of k plus 1, we're looking for that to be 1/3.
Here's the map.
Oops. Series on my phone, k plus 1, and then multiply the k plus 1 all squared minus 1. So essentially in the next step, this here is the solution that we're kind of looking to get towards. And I like to have that in the back of my mind because that helps us work through the next section essentially. So the next thing we now need to have to do is we've got to test the P of k plus 1. Now it's plus 1 because it's the next positive integer. It can change what that is depending on what your situation is, but in this case the next positive integer. And that's going to be the sum of k when I is equal to 1 of I minus 1. And because it's a sum of, we're also adding on the next case scenario, which is going to be k plus 1. So this will be k plus 1 with k plus 1 in here, and then minus 1, like so. Now we can see here that we can actually substitute this section here with this section here using our P of k. We just have to acknowledge that we've used P of k to do so. So in this case, this will be 1/3 of k, the k squared minus 1. And then that'll also add, and I'm going to simplify this a little bit. So you've got this k plus 1 minus 1 at the end here, so that's just k, and that's going to multiply with the k plus 1. So we can just write this as k plus 1 like this. So from here, what we now need to do is, I like to quickly look to see what am I trying to make this look like. And what I can see over to the right is we've got one whole term, essentially, like one product. Where on the left here, I've got two. So I need to connect these together somehow. So I need to, add these two terms together as a fraction. Now, this 1/3 k means the whole, because everything's multiplication here. It means the whole of that first term is all divided by 3. So I can write it like that. I usually wouldn't show this many steps, but I will for the sake of explaining this. But k squared minus 1, all divided by 3. And then we need to make the denominator of this 3, so we've got to multiply the top by 3 to do that. So this will be 3k of k plus 1, all divided by 3. So now that allows us to just add the numerators together, keep the denominator the same. This is k squared minus 1 plus my 3k of k plus 1. And then that's all divided by 3. So now, I'll look over to my right and I've sort of got the over 3, the divided by 3 already. What I don't really have is this common factor of k plus 1 yet. So I've got to look at the k squared minus 1 on the left-hand side because it's the left part that doesn't have it. And I've got to recognize that this is a difference of 2 squares. And we can, let me get rid of that. And we can factorize that to be the difference of 2 squares. So this is k plus 1, k minus 1. Plus our 3k, k plus 1. And what that allows me to do, remember this is all divided by 3. What that allows me to do now is to factorize the k plus 1 out of both sides. And when I do that, I can actually just put my 1/3 in front because I'm just going to have multiplication for everything else because everything's divided by 3 here. So we're factorizing the k plus 1 out. On the left-hand side, we will be left with this product of k and k minus 1. And on the right-hand side, we're going to be left with this plus 3k. And you can start to see that it's looking close to what we need. We've got the 1/3 k plus 1. It's now just this part here that we've got to work out. And we've got this k minus 1 plus 3k. And we need to somehow have a factor of k plus 1 all squared. So what I'm going to do here is I'm going to expand it first. So we've just got this 1/3 k plus 1. And then here it's k squared. Minus k plus 3k, so I'm just going to join that together, so that's plus 2k. There we go. Now, what this here, and this is where I use scrap notes all the time, just to sort of run myself and, I get an idea of what I'm looking at doing. What I've got is this k plus 1 all squared. And you've got to be thinking to yourself, what does that look like in expanded form? Well, this is a perfect square, so it's going to be k squared plus 2k plus 1, which is pretty close to what we have. However, we don't have this little annoying plus 1. So if I want to have a factor of k plus 1 all squared in there, I'm going to have to get rid of that plus 1, otherwise I'm going to change the problem. Now the opposite of plusing 1 is to subtract 1. And you can probably start to see where this is going. So what I look at is going, I need to have this with a subtract 1 on the end to get that to be the same problem. And we can factorize it doing that. So what we're going to do here is going to be 1/3 k plus 1, then factorize this to k plus 1 all squared, and then subtract 1. And if you're sort of worried like you might have changed the problem, you're not allowed to do that, just check to make sure that this will actually expand back out to k squared plus 2k. So if we've got this k plus 1 all squared, take 1. If we start expanding that out, that'll be k squared plus 2k plus 1, and then subtract 1. Then we collect our like terms and we're left with k squared plus 2k. So I haven't actually changed the problem. So from here, I've now proven that p of k plus 1 is true whenever p of k is true. So what we therefore say is p of k plus 1 is true. And we've now proven through mathematical induction that this is true. So we now say, therefore, since the first case scenario was true, which was p of 1, and the p of k plus 1 was true, and I've just realized something that earlier, when I substituted that in, I needed to acknowledge that. So this is using p of k. This is a really important step, don't forget it, like I did. So p of k is true whenever p of k is true. It means that our p of n is true for all values of n when n is a positive integer. And then we've got to give our reason, and our reason here is principle of mathematical induction. like so. So my biggest advice with problems like this is to have a scrap piece of paper alongside of you where you're not going to necessarily show what your thinking is over here in your main working out, but you can start to reason and have a look at what are you actually needing to create to be able to show that the P of k plus 1 is true whenever the P of k is true. One thing to note that like I said earlier, make sure you do not forget the using pk when you substitute that in.